And France. Okay, good. Yeah, we're good.
Well, we could use this.
So it's this thing here, and then just the button when you speak. And I believe this has been fixed. But if you find that it's not responding, you'll have to just come over.
Oh, wait, this is what? This is the...
Yeah, this is the clicker for doing the hand.
Been using the laser camera because folks online can't see it.
Yeah, we won't use that.
But there is a camera. Oh yeah, and we can get. I think.
Oh yeah, she can.
Yeah, I think we. You know, I don't know if you can have. Or maybe it just has to. Okay, cool. Just had to boot up. So, red, yeah, assuming you're not colorblind. Okay, yep. It is red now, which is off, and then when it might be good. If you're going to stand on this side, it might be good to put your mic on the other side. Because usually, yep, that might. Yeah, cool. Yeah. All right, folks, we'll get started in just a sec. All right, so for our last session of the day, we'll transition to thinking about technology maturation of various sorts. And to get us started out will be Lee Feinberg and Laura Coyle talking about the Ultra-Stable Observatories Working Group.
Oh, okay. Okay, great. Thank you. Well, thanks, everybody. I guess this will be a little bit of a change of topic. Now we're going to be talking about technology. But, one of the important questions is not just what is the science, but, is this feasible? What is the technology we need to do it? So I'm going to be representing a very large team with Dr. Laura Coyle. We're going to kind of tag team, so we'll go back and forth a little bit. Talking to you about a roadmap team that we started a few months ago to kind of roadmap out the Ultra-Stable Observatory, and we call it USORT, basically because we're sorting through all of the different technology that we need. Okay, so what is the scope of the effort? So this is a technology roadmap team that was chartered by the Cosmic Origins, or CORE, office. It's actually running in parallel to work that's being done by XEP, and I think Pin is going to talk next about the coronagraph technology roadmap. So this is more from the observatory point of view. It's a very large team. I'm going to show you the team, including industry, including NASA centers, including academia. And at the 20,000 foot level, what we're trying to do is sort of look holistically at what are the technologies that we need, and what is it going to take to get them to TRL 5/6? And if you don't know the NASA lingo of technology readiness levels, TRL 5 basically means that you build some sort of breadboard that you test in a relevant environment. So, way early on JWST, like one of the key technologies was lightweight mirrors, and the relevant environment was taking it to 30 or 40 Kelvin and showing that it was repeatable when we took it cold. So now we're thinking about what is the relevant environment for our technologies, and one of the really important relevant environments is going to be demonstrating it under vacuum for stability, right? So that'll be a key part of what we're road mapping. And this is a voluntary effort. There isn't funding for this really directly. People are leveraging, technology like little iReds or whatever they have. So this is the work that we can do for free. And when there's real money, this will get much more serious and we'll have much better analysis and numbers. And so a lot of what we're doing is actually trying to figure out what are the analyses we need to do, when we do have a little bit more investment. The approach really is being driven by the guidance that came out of the Decadal Survey, that came out of Dr. Clampin's Habitable Worlds Big Picture. I think we heard on Monday Dr. Clampin talk about kind of combining the segmented optics of JWST with the Roman chronograph. We are trying to make this star shape compatible as well, and we're assuming large rocket fairings and making it serviceable. So we're trying to be very broad. We're trying to not rule anything out at this point, but we are definitely focused on ultra stability. That is kind of the key for the observatory. And we're not doing trades here. We're not down selecting technologies. This is more about developing and you'll see samples of it, the structure of the roadmaps that we need and the metrics and the capabilities that we need. Okay, so we've divided the team. It's a pretty large team into 5 groups. So this is pretty broad. You may notice on here things that we don't typically even think of as technology, like verification and facilities. But this is a little bit of the lesson from the early days of JWST, which was we weren't quite holistic enough in our thinking. So we're really trying to think about everything. That's the key point of all this. And we'll narrow down the technology investments, but we want to start very broad and very, very, wide. And again, the key here, though, is identifying the gaps that will allow us to make investments in a smart way. So this is the team of folks. I mentioned earlier that it includes academia, includes industry, includes NASA. We strove really hard to make it a very diverse team. And I mean that in many different ways. Institutional diversity, diversity of having early career people involved, as well as the more traditional forms of diversity that we think about. And I think we've done that as best as we can. We can always do better, but what we have is a really great 5 sub-teams. I've been able to sort of listen in. So these groups are meeting almost once a week, some of them. And there's a lot of the world experts in these topics on each of these teams. And then they're melded with early career people, for example. And it's just been a really positive, very collegial effort. So that's good. And like I said, we've been very broad intentionally, and I think that has also made it go well. By not turning this into trade studies, you're getting more people's voices, and we're able to just be very broad about it. So this is sort of the process that we've used. So we started by defining this work breakdown structure. We're engineers, so that's the way we think about things. And you're going to see from Laura a little bit about a sample of what that looks like. And we kind of broke it down by, different levels, or you can almost think of it as like requirement levels. And then what we've been doing is defining metrics. And I use the example, this is something people early in JWST were very familiar with. One of the main metrics was areal density, how lightweight were the mirrors going to be. And then the capability is the 25 kilograms per meter squared. And so we have now gotten to the point where we have a WBS, we have our metrics, and we're filling in the capabilities. And so you're going to see a little bit of a preliminary view of that when Laura gets up here. But what we realized as we got into this is you can't totally define, like if you want to define an areal density and part of it is mass, you kind of have to know a little bit about the rockets. So the systems team, the one that was being led by Mike Menzel, has been looking at sort of a mass allocation based on what rockets might be available and what the mass allocations might be. And so we're actually finding that the metrics might fall in a couple of different categories depending on which rockets. And so we're having to keep it that broad at this point. But we're finding it's important to think about the rockets even at this early state. And in fact, some of us even went and visited SpaceX and Blue Origins to really try and not start going down a road mapping path and then finding out we were road mapping something that was unfeasible. And volume was the other issue, not just mass but volume. The other area which some of our team, I think Marie Levine, who's part of our team, and Alice Liu, who they were sort of the leads for integrated modeling on Webb and on Roman, they have really emphasized the importance of the error budgets. And we've had a couple of really nice talks, including from Brian Kern, who's from CGI, went through his error budget. Laura Coyle also went through the error budgets that they developed for LUVOIR early on. And so the error budgets and the mass and launch stuff all feeds into the metrics. And we've been getting feedback. Today is an example of that. There's this high contrast workshop in August, which we'll be presenting more details. We'll be identifying gaps. And then the plan is for our team, hopefully, to have our own workshop probably this fall. So we'll use the high contrast workshop to get some feedback from that community. And then this fall, we'll get some more feedback from a larger audience potentially, but it'll probably be an ITAR meeting because some of the stuff is ITAR. And these efforts we're hoping will feed the START and the TAG teams. So we'll kind of brief them and hand some of this over this fall. And if there's other opportunities for engagement, some feedback that you all think would be valuable, please see Laura and I. We're happy to do that. And I think I'm going to have Laura come up and talk to you a little bit about the actual work products.
All right. All right. Thanks for that intro, Lee. So as certainly all of you are aware, and we had a great talk from Carl the other day, we need to have metrics in order to help us define the scope of the work and eventually trade different options, narrow down architectures and more detailed decisions, and come up with what does Habitable Worlds Observatory look like. And so we start at the top with our science metrics, and in this case, many of us working on this are engineers. So we, have just started with something like, the exo-Earth yield of 25. We're going to be relying on many of the folks in this room to help us refine those science cases and have that flow down. But we start with something very broad like that. What is the ultimate science that this observatory needs to do? And then we start moving down in levels of detail as you increase. So we start with an observatory. In order to image an exoplanet with a coronagraph, you need some amount of contrast and contrast stability. Okay, great. What does that mean for the system? That means that you need to have a telescope that achieves some amount of both static and dynamic wavefront error. Okay, so we've basically gone through a number of parts of the system, trying to maintain that holistic view, as Lee said, and identifying the metrics at each level. And as we start at this very top level, we're trying to keep things architecture agnostic as much as possible, and define ranges of performance, so that we know for various constraints, depending on how hard maybe we can push current technologies, we can define what we call like an upper limit, a midpoint, and a lower limit. Then, based on what we know, all the work that's been done for Habitable Worlds, all the work we have left to go, we'll define what do we think is needed for this next generation observatory. And most importantly, that will help us identify technology gaps. Where do we need early investments to help us make sure that we are moving towards a feasible observatory and that we can do so in a cost and schedule effective manner as much as possible. So what our team has started to do is populate both the current stats and what the requirements for HabWorlds are. And as you'll notice in most of these are preliminary values. We're documenting a bunch of the assumptions. As with any process like this, designing a large and complex mission, you have to start somewhere, making your assumptions clear, and we'll continue to refine these numbers as we learn more. And so will depend on things like exactly how we're doing calibration will affect the stability, what kind of launch vehicles we have available to us will affect mass and volume, things like what are our observing scenarios look like, how does that affect the pointing and the stability of the observatory. So all of those pieces are really what we're trying to get our arms around and start putting some initial values in so we can start identifying these technology gaps. As I mentioned, especially at the higher level, we're trying to keep it architecture agnostic. As you start drilling down, For example, this is looking into what static low-order wavefront residuals are in the telescope. So this is things like what is the final surface figure on the mirrors at various temporal scales, and at some point you have to make some assumptions about what your approaches are going to be or more detailed technologies. And so at these lower levels, what we're trying to do is identify the multiple options that potentially exist, as well as bound the performance needs that we might have. If we are talking about mirror surface figure error, is it a 50 nanometer mirror? Is it a 1 nanometer mirror? Is it something in the middle? And what we're trying to get to at that level is to try to write the equivalent spec that Lee talked about for that 25 kilogram areal density, so that we can start to say, okay, if we want to make vis quality mirrors for a segmented telescope architecture, what does that mean? What is our polishing capabilities? How does that affect metrology? So that's just one specific example of the logic that we're applying across the architecture. And as you can see with the color coding, we have these 5 subgroups that are working in these areas. But of course, because this is such a complex system of systems, there's a lot of interaction. There's a lot of talking between the teams that needs to happen. And we need to leverage the work that we're all doing, both within USORT, in close concert with the chronograph teams, and then ultimately making sure that we're traceable to the science goals that all the folks in this room have been talking about the last couple of days. All right, so that's the definition of the metrics. And I think what's clear from that is that an ultra-stable observatory and even an ultra-stable telescope is a system of systems. We've got a number of different control loops that are acting at different spatial and temporal scales, and we have at least the start of a roadmap of how they might all fit together. And so if you start with the simple science path, does this have a laser pointer? You start with light from your science target. It propagates through the telescope and then to the instrument. In this case, it's a high contrast chronograph. So it bounces off of FISMs, DMs, and ultimately gets to your, I'm the first person to do this mistake, maybe. Oh, there we go. Thank you, Vanessa. Cool. Don't press that button. Now that you're all awake again after your coffee break. Yeah, so that is your simple science path of how photons get from the target to ultimately to your detector. And one of the first things that you need to do is use your chronograph to dig your dark hole. And so you have your science image, your higher order wavefront sensor, you have your electric field controller. This helps you determine what electric fields you need to adjust within the entire optical system so that you get that nice area of high contrast. Then once you've dug the dark hole, it's the rest of the observatory's job to maintain that very high level of contrast. And we do so by using loops both in the chronograph and in the telescope. So in the chronograph, there's a number of notional loops, things like the low order wavefront sensor, Zernike wavefront sensors, that give you the optical feedback you need to make sure that you're maintaining the dark hole. Those can operate at different spatial and temporal scales. You can also think about adding things like an internal source so that you can get more photons on your detectors. You can close the loop faster. And so that may provide you some relief to the telescope. On the other side, you can also, there's high-level trades that you can do between the stability needed in the system and in the telescope in particular, and the robustness of your chronograph. There are all kinds of implementation, specific trades there, as well as implications for the science. So that's a lot of discussions that I'd imagine that many of the people in this room are going to be contributing to as we move forward through this process. In terms of what's going on the telescope side, we have a number of metrology loops that are keeping the telescope stable. We have things like a laser metrology truss system that can help make sure that the global positions of the primary and the secondary mirror in the right spot so you don't get beam walk. And it can also control low order modes on a segmented primary mirror. Then for segment to segment motion, which we know is particularly detrimental to contrast in the chronograph, you can look at things like edge sensors. Potentially the Zernike wavefront sensor can address some of these if it can run fast enough. And then you have rigid body actuators to control the motion of those segments and basically take out those perturbations. And so a real question here is that you have all of these different control loops, again, operating at different spatial and temporal frequencies. How do you keep track of making sure that you're attacking all of those different regimes and suppressing them to the level needed so that you can maintain that contrast? Oh, I should mention this block diagram work was led by Dave Redding and John Tesh at JPL with contributions from the members of their team. So again, in order to make sure that we're spanning all of these different domains, this is a control matrix put together by Brian Starsky, and it's looking at what are all the disturbances in the system that we have as a function of subsystem and then component. What are the spatial frequencies they're acting at? What are the temporal frequencies they're reacting at? And then what are our levers or our sensing and control mechanisms to address those spatiotemporal perturbations? And so what she's done is highlighted, again, in this notional menu of options that does have some flexibility in exactly what the bandwidths, both spatial and temporal, are, to make sure that we're addressing the full picture of stability. And one of the things that eventually we'll start to do is look at, not only what the performances of these individual systems are, but how they interact with each other and how we can trade performance in one or the other so that we can achieve the most balanced, practical, and cost and schedule efficient observatory we can that still delivers the fantastic science we're all expecting. I think with that, I'll hand it back to Lee.
Okay. So when we dug into this, we didn't really know where this was going. And as we've been meeting, there's been these very good discussions, and we've kind of been, we call them findings, but we've been learning things as a team. And so these represent, this was a group effort to kind of articulate some of the things we've been learning that I think will be important to future teams that are going to be doing technology and road mapping for this. The first one is that the detailed mission technology roadmaps are highly architecture dependent. So we kind of gave you a scenario with a block diagram, but there's a lot of different ways you can make that block diagram, right? And depending on which way you do, you need different technologies. So we're being very broad at this point, but as you refine your architecture, you're going to refine the technology needs. What we're trying to do is kind of do this from a bounding perspective. Let's make sure we don't rule anything out this early. But ultimately, we'll need to do a whole bunch of studies. The other thing is, we keep emphasizing the importance of being holistic. It's not just about technology readiness level. There's this idea of concept maturity level, which is turning out, is really important. We have a group that does structures and deployments. And when you think of, say, deploying a large baffle, it may be less about technology and more about concept maturity level. And this is kind of harking back to the early days of the Sunshield development for JWST. It's like, can we put more time into maturing the deployment, even if it's not technology, because it's equally important? And likewise, for like a large composite structure or for making mirrors, it may be more about manufacturing readiness levels. This is something that DoD uses. And so we've been thinking in terms of our road mapping, not just of TRLs, but being holistic in those ways. And we need to think in terms of system engineering, like this whole idea of how important the rockets are to drive all these requirements. Another great example is like, how many instruments are we going to have, and how big are the instruments going to be? What volume and mass do they need? That drives then the amount of mass and volume that's left over in the rocket, which drives the aerial density of the mirrors. And so you can't just start investing in technologies without starting with your top level requirements. And then, one of the biggest priorities we need to do is refine these technology roadmaps with modeling and simulation and error budgets. And so we're actually, one of our biggest recommendations of this team for next year and the following year is to do that, is to do simulations, modeling, and error budgeting. It's as important as the actual, we're not saying don't do any technology investment, but why spend a lot of resources on something you may ultimately not need? There's different ways to skin a cat, there's different ways to peel an onion, and there's different ways to build a telescope. And then baffle complexity is actually turning out to be one of the most important considerations of the architecture, which I have to admit I didn't fully expect. The original LUVOIR design had that planar sunshield that was more like the JWST sunshield, but planar. HabEx had a baffle, but HabEx wasn't as big. When you start talking about a bigger telescope, there's a very good chance this baffle will either need some level of deployment or need to be fully deployed. And so that plays an important role, and it relates also to, if you're off axis, the height of that baffle could be as long as 22 meters if you include a scarf. And 22 meters is interesting because that just happens to be the point-to-point dimension of one side of the JWST sunshield to the other. But the JWST sunshield unfolded like this, and now we're talking about a single deployment. that would be that long. And that's big. So that's what a 6-meter off-axis telescope gives you a 22-meter baffle. That was a little surprising. And then the decision on rocket compatibility, as I talked about a little earlier. So I think I'm going to skip ahead. This chart has some other findings, and you're welcome to read these. I think we'll go over these at the August high contrast workshop, but there are a little more details on controls and that kind of stuff. But I wanted to end a little bit on a positive note and a note of perspective. And this isn't really from the roadmap team as much as this is actual data from last week from JWST, which I just thought I would share because it kind of puts it all in perspective. These two images that you see here, these defocused images, one was taken July 3rd and one was taken July 5th. So every 2 days on JWST, we take a wavefront sensing defocused image, and we derive from phase retrieval algorithms what the wavefront looks like. So that's the charts you see on the bottom. The one on the left is July 3rd, the one on the right is July 5th. And, there's a couple things that you can take away. One is, the telescope, this does not include, like, for example, NIRCam, but is about a 65 nanometer RMS telescope, which is already getting pretty close to the requirements of a half-micron diffraction limited telescope that we need for Habitable Worlds. And with just good polishing, we're pretty confident we can get there. So just in terms of making mirrors, we're really not that far from what we need. But the really interesting part of this chart is the stability, because the third picture, which you can barely see, is actually the delta between those two. And if you look at the rate of the drift over 2 days, it's 120 picometers per hour, which is 2 picometers per minute. And we're talking about building a segmented telescope that's going to have active controls that are running at 10 hertz. So those 10 hertz controls are only going to have to be dealing with this type of drift, modulo any sort of oscillatory behavior that's non-zero mean, of which there is some in JWST because we have these heaters that are there for sort of to keep electronics warm. But on an ultra-stable telescope, we probably won't have those kinds of issues. So this kind of sets some idea of, how stable we can expect a large composite structure to hold mirrors, passively. And it gives us some idea of what we're going to need to deal with. And for me personally, it makes me optimistic that this is all very doable. And I think that's it. Thank you.
You, Lee and Laura, for leaving plenty of time for questions. I'm sure there are some. All right, start with Carl and introduce yourself for folks online.
Hi, Carl Stoppelfeld from JPL. Lee, is there an error bar on that 120 picometers per hour?
Is there an error bar on it? Well, let me say this. We've been making measurements every 2 days, so we could probably derive an error bar. I don't know that I know one off the top of my head. But what I can tell you is we haven't actually touched the primary mirror in over 2 months. And it's been getting more and more stable. So I would imagine the error bar isn't that large, actually. It really is extremely stable at this point. It wasn't this way a year ago when I spoke at the SPIE a year ago. I was showing little tilt events that we had. And we kind of knew with a cryogenic telescope, when you cooled it all down, things shrunk, you froze in some strain. And we sort of expected that eventually things would kind of settle out, and then we would see what we might expect a room temperature telescope to be. And so over the last few months, we've been seeing that. And I think there's a couple of papers coming out. I have something in JWST. I think Marshall was talking about putting something in archive. We'll put a bunch of this data out so you can look in more detail at this stuff. We can probably derive some uncertainties. But this is done with phase retrieval. And it's, the phase retrieval, at one point we saw the phase retrieval was good to 100 picometers per, measurement, and this is kind of the delta off of that, over 5 nanometers.
Yeah. So the question was about continuing to fill out the control matrix. So certainly that is ongoing work. Brianne's in the room actually and can probably answer that as well. There she is.
Yeah, so what you saw was a very small portion of that matrix. It's quite huge. But we're making progress, pushing forward and filling it out. It's quite a process. So what you saw, though, was a very, very small portion of it.
how did that tell us to?
Yeah. Well, I mean, historically, we've been, for the big rockets, we've been looking at the SpaceX Starship. We've been looking at the New Glenn from Blue Origin and SLS. SLS doesn't seem to be working as hard on a big fairing at this point, so we're not sure if we're not sure where they're going to be. But we've definitely been talking with SpaceX and Blue Origin, and I think there's at least 2 good large fairings. They're much bigger than the 5-meter Ariane, so that's good news. But one is bigger than the other. Starship is actually, wider. Actually, it turns out the New Glenn is a little bit taller than the current Starship, so part of it is projecting out. So.
Nicolas Flaget, Space Telescope. One thing about the metrics, they are kind of system budget, right? So I would like to advocate for a new system budget when we develop missions like this, not only for the observatory itself, but for the whole mission. And I'm kind of giving a summary of my talk on Thursday already, but you give me the opportunity here to mention it. We need to think about sustainability and the carbon footprint that we're going to have as a mission. I'm going to give details about that on Thursday. Hopefully you will attend, but I think this is a crucial element that we need to add now in designing missions. We need to think about the footprint that we have on our environment. And I would really advocate for adding a line in your table for our carbon footprint.
Yeah, and I think one of the really valuable things we're learning about starting to put these metrics together, error budgets, which they have aspects of the structure that are similar, but certainly a little bit of a difference in the details, is, yeah, what kinds of things do we want to include big picture as we're structuring? So yeah, that's great feedback.
And if I may just, Lee, it's true that for the past at least 40 days, I think the wavefront error hasn't moved by more than 1 nanometer.
40 days?
40 days,
Has
yeah.
not moved
40 or
by
50 days, 1 nanometer.
1 nanometer.
Yeah, very stable.
David Ardila, JPL. Did you do the traceability between the micrometeorite flux and the wavefront errors in detail? Because it would be nice to convince ourselves that we have a budget such that we don't need the baffle. It turns out that the baffle is probably going to be a huge driving element, which I didn't expect it. So have you done the detailed work to justify that?
No, to be honest with you. And actually, that's an excellent point, and I think it's a fair comment that we do need to do. We simplistically just assume we needed a baffle. I mean, we actually know way more about micrometeoroids thanks to the lessons of JWST than we knew a year ago. We did do a test of a ULE little coupon. We've done modeling, simulating a 7-joule hit, which is what we think hit C3 on JWST. But one of the problems we have is we don't fully know what the requirements are of near incident scatter, and how it affects the coronagraph. So we definitely have work to do. One of the challenges is the secondary mirror, right? And the fact that this is all statistical. And so, the hit, a 7-joule hit makes a pretty decent imprint, and it potentially could hit the secondary mirror. And so, so we kind of feel like it's likely to kind of wind up this way, but it is a very fair comment that we really should, given the fact the baffle is turning out to be potentially complex, really do that. And I think Mike Menzel's going to give a talk on micrometeoroids at the high contrast workshop. That'll get a little deeper. And then at the following our workshop, we're going to get into the damage model stuff. So I think you'll get more and more deep of what we know about it.
All right, lots of food for thought. Let's thank Laura and Lee again. Next speaker will be Pin Chen from JPL talking about the coronagraph technology roadmap.
Thank you, Vanessa. So yes, I'm here today to present on behalf of both myself and Luan Puello. And Lee gave a great introduction to together Luan and I co-lead the coronagraph technology roadmap working group. And Lee gave a great introduction on the basic charter, operating principles, of these working groups. And similar to the U-sort that Lee and Laura are leading, this is also a very a large and inclusive group. Right now it stands at about 50 members across different sectors and different career levels. Many participants are in the audience today, folks from Marshall Space Flight Center, Goddard, STS-CI, JPL, for example. And so please consider the entire CTR team as contributors to this talk. So let's start with some big picture. So we've all read this recommendation many, many times from Astro 2020. So I don't need to belabor here, but search for biosignatures from a robust sample of about 25 habitable zone planets. And let's talk about how a coronagraph is going to contribute to that. So in the upper half here, I have the basic sketch of the basic structure of a coronagraph, but we're not here today to worry about the innards of a coronagraph instrument. Let's talk about what a coronagraph does. Basically, very briefly, it takes an image like the one on the left, which shows the PSF of a segmented pupil. Going to clean up all that light from the star and hopefully produce a image on the right where it has sufficiently suppressed the light from the star to reveal the faint planets that orbit around the star. And in this picture, we see 3 planets in this case. And this will also use the image on the right to illustrate just a couple of key parameters about the characteristics and performance of a coronagraph. The first one is throughput. So here we're talking about the throughput of the planetary light. So that points to the signal level. That's the signal part of the SNR. Next one is contrast. That points to the noise part. Contrast is the intensity of the residual speckles in the background normalized by the peak intensity of the original PSF. And then there's another parameter that relates spatially that's very important. Because a coronagraph has to block the central starlight, there's always a central core there where it's opaque. And the outer perimeter of that is signified by the parameter called the inner working angle. So in this image here, for example, I grayed out the inner working opaque zone and shows the inner working angle that's sufficiently small for us to see these 3 planets. Let's suppose we have a different coronagraph with a larger inner working angle, like so. Well, now actually the center 2 planets are no longer visible. We can only see the one on the outer. So it's the case with the inner working angle on contrast. The smaller the numerical value, the better. Whereas the throughput, the larger the better. Okay, so I've already gone through the top 3 points. So another important point to make here is a coronagraph, as far as for searching for exo-Earths, the science product parameter that they really affect is the completeness. So these 3 parameters that I just talked about affect the completeness that we can obtain from the mission. And completeness is the probability of detecting a planet with your instrument, given that the planet is there. And a mission's exo-Earth yield is a product of cumulative completeness and Eta Earth. So where are we right now as a quick synopsis? Let's start with the most controlled environment in high contrast imaging testbeds. And the plots shown here is the vertical axis is contrast in terms of normalized background speckle intensity. And the horizontal axis here is separation angle in terms of lambda over d. And well, it's lambda over d on the bottom, and the top is actual million arc seconds. And I also labeled the circle near the bottom is if we were to look at Earth from 10 parsecs away, and the Earth is in quadrature phase, that's where Earth would be, roughly at the level, brightness level of about 2 by 10 to the minus 10 at 100 milliarc seconds. So you see the best laboratory demo to date, the red curve on the bottom, which was demonstrated at the high contrast imaging testbed at JPL. The lab performance, the contrast level is roughly, it's within a factor of 2 from the brightness of Earth. But the catch here is this is in the most stable testbed in the world. So it's definitely not on orbit environment, let's put it that way. And another curve that I'd like to highlight here is the top dashed blue line. That's data, thanks to Emil Poor at STSCI. That's data from the HiCat testbed right here at STSCI. And next slide, I'm going to tell you something about this capability that's rather unique about this STSCI testbed. So this testbed at STSCI has an actuated pupil that can emulate the dynamical effects from a segmented primary mirror. And this data that I am showing here is where they have injected into their system drift that is that comprise many different spatial modes at the same time. And this is demonstrating stabilizing, and in addition to that, they have a wavefront sensing and control unit working at the same time to counteract and stabilize the effects of the injected disturbances. So the top chart here shows the vertical axis is dark hole contrast. And the bottom half of the chart is wavefront changes in nanometer RMS units. And the horizontal axis is time. So let's look at the top first. On the left-hand side is free running, open loop performance. And you can see clearly the contrast was slowly drifting up due to the wavefront disturbances. And then in the middle, you see a sudden drop. That's when they close the control loop. And I think the enhancement in stability is self-evident here. And the bottom is plotted instead of intensity as in the top, is actually the wavefront and decomposed into different Zernike terms. So again, you see a lot of very, very lively instabilities on the left-hand side. And when they close the loop, the stabilization is clear. Okay, so another I would say a milestone demonstration was done at JPL's high contrast imaging testbed, and this was done by the Roman Telescope CGI team. Here, instead of simulating a segmented aperture, this is a monolithic, specifically the Roman telescope aperture. And the disturbances being injected is line of sight error that reproduces the disturbance spectrum from all 6 reaction wheels that's on the Roman Telescope Observatory. And again, on the left, so the vertical axis is line of sight stability in units of milliarc seconds. And the left third of this plot with a lot of noise is open loop performance. The middle third is when they turned on the feedback control. And then on the right third is when they also kicked in feed forward control. And I think it's pretty apparent the successive improvements in stability. Okay, so you might say, well, you told us a lot about things in the laboratory. How about on sky? This is a plot that's courtesy of Carl Stoppelfeld. It's very rich in information content. I'm not even going to try to do it justice here. So the main point is, roughly speaking, we're here now as far as contrast that we are achieving with ground-based observatories, JWST NIRCam. In a couple of years, RST CGI is going to get us there in that ballpark. And then this is what we're going to need for HWO. You know, it doesn't look too bad, right? We're pretty close. But this is the kind of thing where, you know, the deeper you dig, the harder it is, the more work it takes, all right? So I think you've all heard many times, it's really, really hard, really, really hard. Well, why is it so hard? So again, like Laura said, it's a complex system of systems. So I'm not, all I can try to do today is to give you a flavor, okay? A flavor of the tip of the iceberg. So let's do it. So preface, just for the talk today, okay? Let's assume that a top level science goal is search 100 effective habitable zones. Another way to say that is the mission shall attain 100 cumulative completeness. And that also it shall characterize planets with sufficient spectral coverage to search for multiple molecules. Of course, I'm going to assume a segmented primary mirror with 6 meter inscribed diameter. So let's take a little tour in the vis, UV, and IR. And in each spectral band, I will name 1 or 2 key science cases, and I'm stealing from the LUVAR report. And for each one of these spectral bands, I'd like to discuss 1 or 2 challenges in achieving this top level mission goal that we're imagining. So let's start from the visible. Science case 1, search for exo-Earth candidates. On the right-hand side, there's a blue box taken right out of the LUVAR final report. And I highlight this requirement here, raw contrast of 1 by 10 to the minus 10. And the challenge that I pose here is achieving wavefront stability to enable searching 100 effective habitable zones. Okay, there is contrast. Here I'm talking about wavefront. There's a disconnect, right? Well, that's because raw contrast is important, but maybe not in the way that we normally think about it. It's important, but not necessarily on its own. It's mainly important as an amplifier for the effect of residual wavefront changes. And as Laura did a great job explaining to us, hence, observatory stability, spatial temporal frequencies, observing scenarios, and wavefront sensing control systems are all essential contexts in evaluating chronographic performance. And roughly speaking, contrast stability requirement needs to be better than 10 to the minus 11 between the time scale of when you acquire your reference and the target observations. And even this is assuming that further post-processing will give us another factor of a couple in improvement in SNR. And this is a key challenge for all the wavelengths and science cases that I'm going to talk about today. So since this is such an important issue, let's do a deep dive. Humor me here. So let's say we assume an observing scenario that's akin to that of Roman CGI. First, we point the telescope at a bright reference star, dig a dark hole there, and then we slew to the actual science target star. We observe, we acquire the science image, and we subtract the reference image from it to do background removal. Okay, so mathematically, the science image, I show the equation here. Here, E represents the electric field right after we did the dark hole digging on the reference. And then delta E represents how much that field has changed, how much that wavefront has changed between the time when we acquire the reference and when we acquire the target image. And of course, intensity is what we really care about, and that's field squared. So when we multiply that out, you wind up with 3 terms. The first one is the static raw contrast. That's the intensity of the first image, the reference image that we acquired. The second term is the increase in speckle intensities due to that change in the interim. And the third term is a product of the complex field amplitude of the original reference field and also the change in the field. So that's often called a mixing term, heterodyne term, or cross term. And then we're going to subtract. So that first term, the E squared, the raw contrast is actually removed, at least down to the shot noise level. And we're, approximately speaking, left with the trailing 2 terms. And of the 2 terms, it's actually the mixing term that's the most important. So in this table here, we plug in some made-up numbers just to illustrate that point. So let's say we have a case in the top row in this table here, where we dug a dark hole on the reference, and we wound up with the electric field residual at the 10 to the minus 7 by 10 to the minus 6 level. And in the time when we acquired the reference and then we acquired the target image, it changed by 10%, that wavefront. So you carry through the calculations. The raw contrast is at 5 by 10 minus 11, but that's basically subtracted out. And you wind up, you see that actually that mixing term is far more dominant than the other term. And you wind up with a post-subtraction speckle intensity at the level of 1 by 10 to the minus 11. Now, let's say we have a different scenario where actually the raw contrast initially achieved is 10 times worse. But you're able to keep that field stable better than the first case. You actually wind up with the same final speckle intensity level. So the main takeaway here is that observatory stability and chronograph instrument performance are inextricably coupled. It's in that term right now. It's right there. It's a product. Both things are bundled together co-equally. So we got to think about that as a holistic system. So in the visible, so what capabilities do we need to meet up to this challenge? Well, basically, that's what we just heard about from Lee and from Laura. The USOR group is doing tremendous work on this tremendous topic of achieving ultra-stable observatories and the roadmap to do that. Other important capabilities, actually Laura did a great job, so I don't need to belabor the point here. Wavefront sensing and control unit inside the chronograph instrument can be a mitigation factor. Chronograph dark field control is a technique rather innovative that folks are working on. That involves taking light that's outside of the dark hole in the chronograph instrument and to retrieve information about the optical system and reconstruct the background speckles to further enhance background subtraction. Other than the observatory, if there are significant drips in the DM, deformable mirror surface figure, that can be a significant contributor to instability as well. So there are techniques people are developing that use wavefront sensors, for example, Zernicke wavefront sensor inside the coronagraph instrument to do real-time monitoring of the DM surface. And science case 2 is spectral characterization. I see that time is running low. I better go faster. And so here specifically water and oxygen measurements. And in the red box, I show the requirements. R equals, for oxygen, R equals 140. Signal to noise ratio greater than 8.5. And the challenge I list here is attaining low enough detector noise to achieve requires SNR for retrieving gas abundances. And basically, again, I need to go through this quickly. So Bijan-Nimadi recently did an analysis of error budget for exo-Earth characterization with 6-meter telescope using an IFS. So one fun thing is that IFS requires a high number of pixel sampling. And that all those pixels really, the individual noise starts to really add up. So he, in fact, could not close his error budget for SNR greater than 5. So at least on paper, is not meeting the 8.5 SNR requirement. And in the error budget, dark noise is the dominant term in the detector. So obviously, further development of detector technologies. And also there's some possible traits as far as what kind of spectrographs is optimal and what kind of spectral requirements versus science return. And let's move on to the UV. A very important science case there we heard this morning is ozone detection as a proxy for the presence of O2. Now it's going to tell you whether or not there's O2 or not, but not necessarily how much O2. And so the challenge I list there is, again, achieving an adequate wavefront control and stability to achieve the requisite contrast stability. So I'm repeating that here mainly to illustrate that at shorter wavelengths, that gets even harder. Okay, so for the same wavefront change in physical dimensions in terms of phase, it's larger. And intensity is field squared, so spectral intensity scales as 1 over lambda squared. And I just want to have mention a couple of different additional things that we've been worrying quite a bit about in the UV band. One is the impact of low UV throughput. Using fairly conventional assumptions about the number of reflections in the coronagraph and aluminum coatings and whatnot, you derive a system throughput of only 3%. And as we know, in the UV, there are fewer bright sources compared to the visible. So it begs the question, how many viable UV targets are there? And thanks to recent hard work by Eric Mamajek, Karl Stoppelfeld, and Dmitry Savransky, actually, I have to say I'm pleasantly surprised that it indicates only a modest loss compared to the UV, to the visible target list. About a quarter of the targets are lost in this comparison. And of course, not surprisingly, the loss is mainly in the cooler stars. But this work is still preliminary. I pop up their most recent results, and I'm sure when this is fully vetted, they're going to release this publicly. Another thing that we've been worrying a lot about in the UV is polarization aberration, which gets much worse for shorter wavelengths. And so the upshot there is that nature actually offers us a natural mitigation. Most UV targets are at large working angles. The effects of polarization aberration mainly projects onto low-order Zernike modes, such as astigmatism. So the effect is most pronounced at small working angles. And nature is presenting us to access larger working angles. So there are ways that we can optimize coronagraph designs to mitigate that. And the final case is IR detection, and the case I list here is CO2 detection. To move along quickly, here detector noise is a challenge as well. And a little different from the visible case is that here, instead of the dark current, read noise is actually the dominant term here. So for detectors cooled to temperatures below roughly 120 K, read noise is typically orders of magnitude larger than the dark noise. So obviously, we need to develop better detectors here. So some parting comments. As mentioned several times today, different spectral regions have different challenges requiring different solutions, different instrument configurations, and different observing scenarios. So spectral coverage is a key trait to be conducted. And as I keep saying, observatory coronagraph must be considered and designed holistically, which is what we're doing between the two working groups. And wavefront stability is critical. And one thing is that if we're using natural guide stars, photon radiation imposes hard limits on the attainable control bandwidth. And Laura already talked about the different systems that will be helpful, that's needed. But things that I haven't had time to talk about, things like high fidelity integrated models, post-processing techniques, manufacturability of optical components, they're critical as well. Test facilities. One day we will need to demonstrate broadband coronagraph performance in vacuum with a dynamic OTA simulator. And NASA, you've all heard about standing up many groups to rise up to these challenges. Maybe the final comment I'd like to make is that we are NASA. We do things not because they're easy, but because they're hard. Thank you.
Maybe we need a little inspiration at the end of that long list of challenges. Maybe I'll start. Is there anything on? Okay. How about in the room? Must be some initial reactions or questions. Yeah.
Thanks. Very nice, comprehensive talk. Steve McCandless, Johns Hopkins. Just to be a little snarky, should we be worried?
We're always worried.
No,
when are we not worried? We should be worried and optimistic at the same time because it's hard, but is it worth doing?
Yes.
Thank you. Then let's do it.
It's definitely worth doing. I'm just worried about the delta E, as you pointed out, it seems to be more critical than contrast, and that seems to, or at least as critical, and that seems to be not very well appreciated. And thank you very much for pointing that out.
Well, I actually thought Lee and Laura did a great job on that, but
to see it mathematically is very important.
Oh yes, thank you.
We have one question online from Sasha Hinckley. She had a question about the plot early in the talk showing contrast curves from several different test beds. It looked like the best performing one, the red curve, was from 2019, and all the poorer performing ones were more recent. Have the more recent test bed runs underperformed since 2019, or did I read that wrong?
Well, a great question. Just to let the person know, there was you aroused great laughter in the room, which is great at about 5 p.m. here. So there's many parameters that go into different types of coronagraph design. The testbed environment, whether it's in vacuum or in air. Sorry, this is, a plot is necessarily oversimplification. So I wouldn't draw any conclusions from this chart as such.
All right. Thanks very much, Pin. And I'm sure there's going to be a lot more discussion to come. And our final talk for today is from Kevin France, who will perhaps solve some of those problems with UV throughput. We'll see.
Yeah, I think that's a different UV throughput. We'll solve it at the telescope level. Good afternoon. So I'm Kevin France from the University of Colorado. When I saw that I was giving a technology talk after 5 o'clock, my first reaction was, oh no, this is going to be the sleepiest crowd ever. But in fact, so I had started with a community engagement portion of the talk, and we're really going to start easy to get everybody fired up. But seeing that we were just laughing, I'm going to actually skip ahead and talk about what I was supposed to be talking about. But I do want to start with a community poll. So actually, I'm going to skip through all this right now. Yeah, okay. So I thought it was 5 o'clock. I mean, come on, but you guys were just laughing. So I want to take a poll of the room at what wavelength should we set the short wavelength cutoff for the Habitable Worlds Observatory? And it's going to be a multiple choice question. You can choose something else, but you'll be wrong. So, okay, should we set the short wavelength cutoff at 400 nanometers? Yeah, okay, right. 200 nanometers? Yeah, right, okay. 120 nanometers? Or 100 nanometers. So, all right, by show of hands, maybe option 4? Okay. 10 nanometers, it's a totally different telescope. Okay, great. So your feedback is important to us, and I appreciate that. You will be receiving a survey later by over your. Okay. So I was asked to come and talk about what are the technology tall poles for enabling a UV instrument for habitable worlds. And so I'm honored to be asked to do this, but this is actually the work of a huge group of people that have been working on technology and roadmaps and things really starting over 10 years ago. So a lot of people contributed to what I'm going to talk about today. So I'm going to start with what we know already, that the decadal survey gave us these 3 science themes, and from that we were recommended to have a Twiddle 6-meter telescope, because it touched on all 3 of the primary science themes. And all 3 of those primary science themes also have needs for ultraviolet spectroscopy, and some for ultraviolet imaging. There we go. Okay, so, and I'm just going to speak to this for about 2 slides because it's been covered really nicely earlier today. So Chris spoke about the importance of probing multiple sight lines to understand and tomographically map the circumgalactic medium around galaxies. So, this requires high sensitivity, high resolution ultraviolet spectroscopy, and multi-object capability to be able to do all these things in a single shot. Similarly, if we go to one of the different science themes from the decadal survey, like worlds and suns in context, we have the ability to use high sensitivity, multi-object, high resolution ultraviolet spectroscopy to survey star-forming regions to actually build up maps of the composition of planet-forming disks where these exoplanets are forming. With this capability like that we imagined for HabWorlds, you could basically outdo everything that Hubble has done in the area of young stars in its 33 years in the course of a couple of tens of hours of programs pointing a multi-object spectrograph in one of these star-forming regions. Okay, so the science need is pretty clear. So what I want to focus on is what type of instrument do we need and how do we get there? So fortunately, the recommendation from the electromagnetic observations from space panel 1, thank you, Evgenia, made this pretty clear what we needed. They said that we needed to get imaging and spectra from the range of 100 nanometers, so you were all right, to 2 microns. And they said that we should be thinking about things that are similar to the instruments that were designed for LUVOIR and HabEx, so I'm going to talk about those in a minute. And then we need to have moderate to wide field imaging at UV wavelengths, and then multi-object spectroscopy. So that's going to lead into kind of what I'm going to talk about today. So this instrument doesn't have a name yet because we haven't designed it yet, but I've been calling it the Habitable Worlds Ultraviolet Multi-Object Spectrograph because this just comes off the tongue easier than saying that every time. So what we're going to talk about is, I thought about that, yeah. Too many U's. So I'm going to talk about how do we leverage our previous investments, and really that's going to be the work of the LUVOIR and HabEx teams. I'm going to talk about overview of our key technologies we need, and these are going to be more at the component level. And then I'm going to make some recommendations and discussions about what we need for laboratory and prototype instruments to demonstrate these things. And one of the things that's going to come up kind of time and again here is getting early career colleagues engaged in this process, basically starting today. So it's really nice to see the ECR focus here at this meeting. Okay, so what have we done already that we can use? So we've also seen that we know that this was the 6-meter inscribed mirror. And as Aki said in her closing talk yesterday, that the 6-meter inscribed mirror is not drastically dissimilar from the 6.7-meter inscribed LUVOIR-B. So it's not that we haven't thought about instruments and what they need at this size scale previously. So, of course, and I mean, we say this again and again, the instruments and the missions that were designed for LUVOIR and HabEx are not habitable worlds, and they're going to be different, and we're going to need to do all the studies again, but we should also not throw out the knowledge base and all of the design and study experience that was generated over those 4-year studies. So I wanted to just take a second to kind of give you an overview of the instruments that were conceived of for LUVOIR and HabEx, because I think that they were examples of instruments that were designed with community-driven science input in mind. And so they're going to be, I believe, representative of the types of requirements and measurement needs that we're going to need for habitable worlds as well. So I'm going to focus a little bit more on LUVOIR because that's the one that I was involved in as part of the study process. This is the LUVOIR-B spectrograph here. It has 3 channels, low and medium resolution, near UV, far UV, and optical multi-object spectroscopy over a couple of arc-minute field of view. And again, I'm not going to speak to all the ones that were in the HabEx UVS. They're all in the same family. One of the things that was on LUVOIR that wasn't on HabEx is the FUV imager, multi-band UV imaging, a similar field of view. And then something that we don't have actually here in this particular diagram, but a high-resolution point source UV spectrograph that would be complementary to the polarimetric capabilities of the Pollux instrument that was studied for the LUVOIR study. So these are the modes that we imagined for a UV instrument. Again, probably evolved somewhat for habitable worlds, but I think this is an interesting place to start. So we talked about resolution. Now we know that we're going to need high sensitivity. And so here is a comparison of the LUVOIR-B effective area curve. This is one metric of sensitivity, and that's shown compared here to the state-of-the-art on the Hubble Space Telescope today. As Chris noted in his talk, something we don't talk about very often, but the near UV throughput of HST is not that great, and this is actually probably a gigantic growth area for high redshift or intermediate redshift galaxies to do the type of spectroscopy that we have typically only been able to do in the low redshift universe. Of course, we'd have loved to have the LUVOIR-A effective area curve, and so Vicky had this on her thing this morning about missing LUVOIR-A, but this capability is still very, very impressive. So how are we going to do the multi-object spectroscopy? Well, we probably are going to be doing it with microshutter arrays. So this is an example of the next generation MSA development ongoing at Goddard. So basically, this gives you a grid of approximately 800 available shutters in the focal plane. So you can open them through dynamic control and take spectra of several hundred objects in every field. And then within each shutter, because they have this kind of long slit shape, you're actually doing long slit spectroscopy in every shot. So this is a huge multiplexing advantage compared to what we have previously, which is all single object spectroscopy, except for perhaps thinking about the long slit spectroscopic capability of STIS, but it's really a different capability than this. So, what are the specific technology needs for habitable worlds? And I put this asterisk here because while HabWorlds needs this stuff, all of the technology development that we do for habitable worlds all flows down to all of NASA's other missions too, from probe level, explorers, all the way down to Pioneers, and even CubeSats are now using things that were originally sold as technology maturation for large missions. So we need it here, but it really does have a trickle-down effect. Okay, so I'm not going to go into great detail about these. I'm just going to kind of mention a few of these. I'll hit a few highlights of what's been happening through the process, but then I want to make sure I get onto some of what we need to do for future work. So the things that we've been talking about are high-efficiency spectrograph design, large format photon counting detectors, optical coatings that go down into the far UV but continue to have high reflectivity in the visible and near IR, multi-object selection, band selecting filters for FUV imaging, and then development of gratings. So when I go through this, because I'm a technologist at the University of Colorado, I'm probably going to be a little heavy on the pictures of things that come from the University of Colorado, but I'm going to talk about stuff that comes from all different groups. And I've got a few tables in here if anybody wants to get the slides later to get kind of a broad overview of what's being done in state of the art. Okay, so what about spectrograph design? So we did that already. We know how to do this, right? So this is again the Lumos design from Louvois. It started as a ray trace. It became a CAD model. As Julie mentioned in her talk, there is a many 1,000-line MEL, so we even have equipment lists for what you would need to do this. We have gratings with groove densities. After we designed this, we went out and actually got quotes for this stuff to figure out if it could be fabricated today. We designed new grating selection mechanisms. We did thermal analysis. We even included the mass of the wiring in the stack-up. I mean, this type of instrument concept has really been studied very well. We've even done performance designs where, you can basically pick the wavelength and the resolution and spectral and angular resolution as a function of where you are in the field of view. So you could do detailed target simulations. So I'm going to suggest that while we need to be investing in the people and the time to do the design studies after the science requirements are refined for HabWorlds, we know how to do this one. So this is something that I feel that if somebody gave us a new set of science requirements, we could put the right group of scientists and engineers in a room and fix this one. So all of the rest of them are specific hardware requirements. I'm not going to walk through all these charts in every one, but I put them in here if you want to see them later. So this is capturing the needs. This is a combination of things from the core technology gap list and things that were identified by the Louvois and HabEx teams. So I've kind of merged them into a single set of requirements here. And in this column that you'll see as I kind of flash through these, is ongoing or recent investment, most of this coming through the SAT and APPER programs. So these are competitive through ROSES. Okay, so we're going to need big detectors because the focal plane is going to be really big if we're going to do high-resolution spectroscopy over multiple objects with a big telescope. So just to give you a couple of ideas about where we are with the state of the art, at the shortest wavelengths, we'd imagine using photon counting microchannel plate detectors. Here are a couple examples of large format. This is 8 inches by 8 inches on a side in a single detector. That's enormous. So we're able to get to beyond 8 inches on a side right now with pretty high quantum efficiency down in the far ultraviolet. There's still technology development to do here, though, because these large detectors don't yet have the spatial resolution that's required to support high resolution at all these wavelengths. And at this size scale, they also still don't support the count rate requirements. There's a technology path to get there, but it needs to be scaled to this size. I'll also emphasize that, particularly for the near ultraviolet and the optical channels, the work being done at JPL to develop the delta-doped CCD and CMOS devices is really spectacular. This is something that Shirley and Nixad provided for me from something that they just developed for, or maybe not just developed, but recently developed for the Europa Clipper. And then there's a SAT effort for UV optimized CMOS that was just selected last year. So this is good work in progress. Optical coatings. There we go. So we've now taken these lithium fluoride coatings, these enhanced and protected lithium fluoride coatings, and taken them from the laboratory and deposited them on large flight-size optics, and have used them on flight missions. So I'm going to show you some quick results here. This is a really nice example of collaboration between the academic institutions, Goddard and JPL, where we all contribute a piece of this. So this is an optic that was flown on one of the Colorado sounding rockets. It was coated in the enhanced lithium fluoride at Goddard, taken out to JPL to do this very thin capping layer that makes it less environmentally sensitive, and then integrated into one of our rockets. So this is now also being done. Somebody mentioned this morning, I think Evgenia mentioned this morning, the Sprite CubeSat. So this is a reflectivity curve from the Sprite CubeSat. It looks good in the optical too. I just don't have it on this chart. I know, Aki told me don't show any more reflectivity spectra that don't go out to the optical, but I don't have it on this plot, but it looks good. So what you're seeing here is, so this is the raw reflectivity of the lithium fluoride as deposited at Goddard. And then we take it out and we put this thin capping layer on it to protect it from the environment. And you get these solid curves. So it suppresses it a little bit. It's a couple of % effect. But then we took these optics and we put them in a humidity chamber at 50 and 60% for a couple months. And what we're finding now is that these things basically don't change when you do that. And that's always been the boogeyman about lithium fluoride, that if you use lithium fluoride, it's going to have these huge environmental challenges that you can't work with it, and it's going to be prohibitive from doing it on a large mission. So we're figuring out how to do this, right? These are on small optics right now, and it needs to be scaled up, but we're learning how to do this, and the results are really promising. Similarly, this is one of our rocket optics. So this is an optic that we coated in 2018 and measured it in 2018. We flew it in space 3 times. We took it all over the world. We took it and put it out. We let students touch it. We put it on a boat from Australia for 6 months. And this is the degradation that we're measuring now. So it's above 1,100 angstroms or so. You know, it's a couple of % loss. And this is comparable, right, to what HST lost, what HST cost lost on orbit in 4.5 years, right? And this is a really harsh laboratory environment. So these coatings are really holding up very well. I think this is very promising to our ability to do it in an ambitious UV instrument, but also do things that are compatible with the high sensitivity required for the coronography. Okay. Microshutter development. So this is part of the SAT program led by Matt Greenhouse, I think, at Goddard. So this is ongoing. I believe they were just selected again recently. And again, a good synergy with the sounding rocket program. This is a smaller version that they're developing for flight testing on one of Steve McCandless's rockets that I think will launch next year. Yeah, where they're actually taking these and using them in their intended purpose, which I think is a key point that I'm going to come back to at the end of my talk. So a lot of advancement here. I'll also say there's been some good advances in micromirror arrays, but I think that the technology readiness is not quite there the way that it is in the development with the MSAs right now. Narrowband filters. So Emily Farr showed this very quickly in her slides yesterday. So we're developing these narrowband filters for far UV imaging. So for instance, we saw I think in Chris's talk, the image of the low redshift oxygen 6 halo around a galaxy. Right now we do this with a combination of filter subtractions, but if you could just go out and take a direct image of it and not have to worry about these multiple red leak subtractions, life would be easier. Also, having a 6-meter mirror makes it easier. But basically, this is work in progress to develop these filters now. And then the last thing that I want to say is about the diffraction gratings. So a lot of work being done with electron etching, both for shaped gratings as well as shell gratings. So here's some work that shows recent results from 2 SAT programs, a combination of Penn State and Colorado and Johns Hopkins. So this is shell efficiency, groove efficiency now, and for comparison, this is roughly the groove efficiency of the gratings that are flying on HST right now. And so it's a two-pronged win here, because not only is the efficiency 2.5 times higher, all the efficiency you're lost here goes into scatter, right? So it not only is lower signal, but it increases the noise everywhere. So this efficiency gain, it's really it's more than a factor of 2.5 better for high resolution spectroscopy. Okay, so those are kind of the individual component technology that I think is going to be important. Do we need to be thinking about this in GoMap? Yes, please, let's fund it as soon as we possibly can. And there's going to be a couple of avenues, or a couple of, I guess, boxes that this falls into. There are a few things that continue to need what I might call materials physics development, where we're still actually refining the process of how to do this. But a lot of these things, for instance, I think the coatings now, we've figured out the material physics, and now we need to work on scaling these existing technologies to larger sizes that we're going to need for habitable worlds. And then one step beyond that, we're going to need a lot of everything, right? There's going to be a lot of mirrors. There's going to be a lot of gratings. They're going to need a lot of detectors. And so right now, we're really working in the model of every component is a research project. We have to move beyond that and be thinking about how to mass produce these things, where we can then, have 30 mirrors that are being coded in succession, and clear coding in assembly plan. I need to be thinking about these things as a system. So that's going to bring me to the second to last thing that I want to talk about, is that, so we're talking about individual components, right? But this is a system, and this is a pretty complicated system, and it really needs to work as a system, and all the different pieces are going to contribute their own little sources of error to the system. And I would argue that the only way to understand how this system works together is to actually build something that works like that system and see how it goes. There are a handful of examples that one could think of where detectors behave differently once they've been put on orbit. Gratings don't work quite the way you expected based on individual pencil beam measurements in a laboratory. And the only way to find that out is to develop a prototype system. So I'm going to argue that we need to invest in prototype systems. And if we're talking about getting into pre-phase A or phase A in 2029 or 2030, we better do this really soon, because we're going to run out of time. So step number one would be an investment beyond the current APRA levels. Don't mess with APRA today, just beyond APRA, in suborbital missions. So this isn't just my opinion as someone who does this. This is what Astro 2020 said. They said many of NASA's visions, technology, and expertise developed through the suborbital program, and then crucial for maturing technologies. So we should, just like we're taking them at their word for what type of large mission we should do, we should adopt this plan for their smaller missions. Laboratory and testbed instruments. This is what the high contrast imaging folks have been extremely successful doing. And so one might imagine that we should start thinking about building prototype instruments where we can see these things operating together. And then the last one that I want to really touch on here is going to be, but I think is complementary or similar to what Evgenia was talking about this morning, with a suggestion that we need a new type of small mission that allows us to combine technology development, instrument testing, and probably even a little science to not just mature the technology, but also to bring people into the field, because these are going to be the people who build the bigger instruments later. So I would argue that the Pioneers missions that we have now, about $20 million, could be a really great way of doing some technology development where we build a whole system and we try it out as an instrument, we put it in space, we see how it works. But budgets are tight, and Pioneers, right, technology development is actually kind of discouraged. And, as a current small-sat PI, right, we're usually just trying to survive to get to the launch and get things together on time. And so to maybe take the Pioneer analogy a little bit too far, I feel like this is kind of the feeling that you're always looking behind you, because you're just trying to get there. Similarly, and this is maybe going to be a little controversial to say, but the SAT program provides a model for testbed, for technology development that could then be integrated into missions, but sometimes we get a little siloed, where SAT programs, not all of them, but some, focus really on a small set of requirements that were developed several years ago and are really focused on doing one or two things in the lab. So what my suggestion would be is to merge these silos and do something where we go beyond pioneers to homesteader. Thank you. Okay. So what would this maybe look like? So I made up a pretend example, and I see I'm running out of time, so I'll be quick about this. So you imagine that this is Homesteader 1, H1. And so this is going to be a mission that is a prototype multi-object spectrograph. It's going to scale up the coding technology. It's going to flight test an engineering model microshutter array that they're going to give us. And also do a local galaxy survey, a spectroscopic galaxy survey that would be an analog to something we do at higher redshift with Habitable Worlds. So we're going to get the technologists and the instrument designers and the early career professionals together, and they're all going to come up with a plan. There's going to be an interaction of the science, technical, and implementation teams in a way that breaks down some of these silos that I was just mentioning. We're going to scale up beyond our current capabilities for coatings. Right now, we've never deposited a full AL ELIF with the current way that we would do it for a bigger mirror to a modest size to demonstrate we can do it, but also something that could be used by this mission. And then we're going to figure out how to do this capping layer at this size, which has also never been done, but is probably just a scaling process, an engineering challenge. We're going to deliver that mirror to the H1 team. They're going to assemble, test the payload, get it ready for delivery. They're going to have early career people, graduate students, postdocs, early career engineers, and project managers, like Evgenia was talking about earlier, and they're going to be ready to launch this thing. At the same time, there are going to be lessons learned from this process of figuring out how to do this for the first time. And so they're going to incorporate those lessons, and they're going to go and scale up to, say, one more step, and then the of order 1 meter type mirror that we're going to want for Habitable Worlds. So then they're going to go through a test program, but this test program is not going to be made up of some requirements that were generated 5 years ago and from some NASA document. They're going to be actively informed by the experience that this group has had trying to test this as a system and figuring out what are the real-world challenges of working with these coatings. And that's going to inform how we make a better reflectivity uniformity test, the test plan, and an assembly plan for Habitable Worlds. Then we're going to launch H1. We're going to do the preparatory science. And at every step of this process, these teams are going to report back to the start, or whoever becomes after the start, and whoever becomes the pre-phase A Habitable Worlds team. So it's part of the Go map. It's interacting with the various teams that are working on the larger mission while doing the technology development and the early career training. Thank you. So I'm going to guess you can do this for about $50 million. If you're curious, you can ask me why I picked that number later. And importantly, you see that I have early career leaders, early career people everywhere, right? So we're going to get engineers, students, postdocs, and they're going to start the project like this, like my son's baseball team, and they're going to end the project being the leaders that we need to do the full implementation of Habitable Worlds in, the 2030s. Okay, I see that I'm about out of time. So I think this bit about the early career part is important. So I'll just end with a slide talking about the people here. And again, this is my own personal research group bias. But this is a slide that shows the students, postdocs, and early career engineers that have come through the various suborbital projects that we do at Colorado. And this is just in the last 6 years. So these are people that have been involved, right? There are a handful of them that are in the room today, and that's wonderful. And they're all working on NASA missions now in some way, shape, or form. So I say it when I give talks to people who come to the university, there's no program where we allow people to jump in, get their hands dirty like small missions. And that could be balloons, that could be rockets, that could be small satellites. But these types of programs, I think, are a real avenue for advancing technology, getting people in to do technology and science, and get them excited about being part of, spending 20 years of their lives engaged in this process. Okay, so I am really out of time now, so I'm just going to go ahead and leave this last slide up. So I think our charge for the next couple of years is to advance these component-level technologies and then begin to think about how we scale them up using a combination of laboratory and flight instruments. So thanks very much.
Thanks for a strong finish to the day. Got time for a question or two if we can stay a minute or two late.
Hi, Carl Stoppelfeld again from the NASA Exoplanet Program. A comment and a question about coatings. During the HabEx study, there was a wavefront simulation to show that the fluoride overcoated aluminum would be compatible with optical coronography in terms of the wavefront, the phase shifts that are induced, the polarization, and so forth. Although we have never done any overcoated aluminum in the high contrast test bed. It's only been bare aluminum. So it'd be nice to confirm that calculation with a real demonstration. But my question is about the lithium fluoride, where we haven't even done the numerical calculation yet to show that that coating is compatible with coronography and the optical. And then we'd have the same question about doing a lab test. So I just want to ask for your intuition. Are the indices of refraction or the polarizability for lithium fluoride very comparable to mag fluoride? We shouldn't worry, or is there a lot of difference that we have to work through?
Yeah, so that's a great question. And the answer is that the back of the envelope calculation from just the optical constants suggests that they're very similar. If not, lithium fluoride might be even slightly better. But I wholeheartedly agree that we need both a modeling and a laboratory study that validates this. And so there's a UV, is Sarah here? There's a UV instrument group that is being spun up through a core that one of our goals is to address this exact problem, is basically do a trade study where we work with the coronography experts to understand exactly what the uniformity requirements are, what the polarization limits are, and then we do that from a theoretical perspective, but then also do the demonstration with actual coatings. I mean, I would argue that, right, it just hasn't really been demonstrated with any coating. And so, yeah, I think this is something that needs to be done, but that's going to be one of the first action items for this UV technology group.
Okay, maybe one final question for the day, and then Jason will have a word, so don't leave.
I'm Shingo Kameda from Rikyo University, Japan. So I have a question about MCP. So you were talking about gallium nitride MCP, but the slide you showed about MCP is gallium nitride or CSI? Or...
The ones that I showed was CSI.
Okay.
Yeah.
Okay. And the peak efficiency is 60%?
50%.
50%.
Yeah.
Okay. Thank you.
Mm-hmm.
Well, let's thank Kevin again and all of our speakers for this session.
It's 5:35. I really don't want to keep you very long, but thanks again to all the speakers for the day. Excellent talks from start to finish. I learned a lot. That's what we're here for. I hope everybody's having a good time. The only real practical announcement is that we're going to do a conference photo at the end of the morning sessions tomorrow, right before lunch. So that is not the time to make your escape. Please keep going. We'll go out on the front steps and we'll have our traditional conference photo. As we've said today, you will want to remember this by being in the picture. So please plan. Otherwise, you can't prove you were ever here. Please plan to be in the photo right after the end of the morning sessions tomorrow. And we'll see you tomorrow morning. Thanks, everybody.